So we're gonna open a PIV project which is here. We can look at it. It has two figures. It has raw images. It has 263 images of an experimental dataset which have been rectified. So another 263 images. And we have calculated vectors. Okay, so now I would like to show how we can export figures out of this project. So I'm gonna start TecPIV from the shortcut on the desktop. So here we start our MATLAB session. Go to our TecPIV folder. And find the available workers. We have found 6 workers on this workstation, and now we open the main window as it was last time. Oh no, that's the new one. So now we open this already existing project. So project open, it's on the desktop, and I select the MATLAB file, maths file. And now it's going to open the two figures. Alright, so this is how I left the two figures last time. Alright, so now we are in the dataset row, rectified with the vectors. This is our image number 2, for which we have tiny vectors. So we can decide to go to image 50. And we have updated the image. So what we have in this experiment is that all this part of the model is pushed at a constant velocity by the piston, which is here. On the other side there's no movement, and the movement is accommodated along two fold zones, one on this side and one on that side. Alright, and what we have now is we see the vectors at this moment. We have the scale here, 0.1 millimeter per second. Okay, so we can put image 100. Alright, so at image 100, all the deformation is accommodated on this fault zone, and we see that we are saturating the color scale for the strain. So the color here is the derivative of the vector field, and it goes from minus 0.015 to 0, negative because it's convergence. Okay, so if we want to display the amount of convergence, we may want to change the color scale. So display setting. Alright, so here we have a scaling mode of the vectors. So this block here defines how the vectors are displayed. We are displaying every 4 vectors, and we have a reference vector of 0.1 millimeter per second. The derivative is displayed with EXX, so the convergence in the horizontal direction on that screen. And we have an arbitrary range between the minimum here and the maximum there. So let's put a minimum that's a bit lower, apply. Okay, now we start to see areas. It's just very concentrated, so we won't be able to to see much more than that. The strain is really concentrated into a narrow band. So what we want to do maybe is change how many vectors we have, because with vector grid factor of 4 we have a number of vectors, but they end up being pretty small when I export an image. First I'll show what it does. Okay, so we leave it like this. We're gonna export this image. Display, export this frame at number 100. Okay, so here I can see that it has created a file named row rectified vectors image 100, and I can see it now in my project. So I'm going to use the Windows Explorer to check this out. Okay, desktop. Now I have a PDF file here. If I open the PDF file, this is the figure that has been created. So it is a nice high resolution image of our image at that moment. It has the color scale, it has the scale for the vectors, and we see that the vectors are pretty small. If we reduce that figure for publication, the vectors are going to be too small. So we want to have fewer vectors in order for these vectors to be bigger in the figure. So I'm going to go back to my main figure and display setting, and I'm going to show fewer vectors, maybe 1 every 8. Okay, so we have fewer vectors and therefore they appear bigger. Maybe this was not sufficient. 1 every 10. Apply. Okay, now we have fewer vectors, which of course appear bigger. We see that the color limits are not really lining up well with our information there, so maybe we can change the setting here. Let's see if I change it like this. Alright, it's a little bit easier now to read the color scale. Okay, so now we can again export this frame, and if I go back to my project, okay, the image has been created. I'm going to check the main window. It has been created. So this is my new image. The vectors are a bit longer. The image is better for use in publications, for example. Okay, we have the corrected image, we have the vectors, we have the derivative, we have everything as it should. Perfect. And this can be used now, can be opened into a profile like Inkscape. I'm going to open Inkscape. So I can also open, indicate that I want the image at the time, say 1000 instead of 900. I'm going to enter the time that I want, and that is, the closest is number 102, which is apparently exactly 1000. Okay, so now we have our Inkscape vector drawing software. I'm going to drag the PDF, clip to media box, and import via Poplar. Open. Done. We have in a vector drawing package our image. Now I can ungroup all these elements and select this, regroup because I don't want the background. Okay, now we have a figure which is only the meaningful part, and I can scale it to any size I want to create a good quality figure. Okay, let's close that without saving. We don't need that. So we have image at time 1000. We can go to 500. Okay. We can export this image just to show you again how that works. So if I go back, now we have also this image 52. So the image is the number is the image number, not the time. However, it's not in this one. It's only when it's exported in a batch that it gives the name. So this is the some of the other options that I will show now. One thing we can do is put a number below the minimum. So let's say I want image number 0. It's not possible because our first image in the dataset is image 2. Okay, so we set 260. So let's ask for an image 300. That's our last image, 263, at which point we had stopped the convergence and we kept recording, so there was almost no movement. Okay. What we can do as well is use the slider to go to a different position. So here we end up at image 200 using the slider. Still 201. I can move to any time. Okay, and we have a constant scale for all this dataset and a constant vector scale for this dataset. So what we can do now is go back to 0, which is going to be 2, okay, and ask the system to export all the frames. So when we export all the frames, we have a number of settings that we can use. We can export as a movie, which can be used for presentations. We can export as individual PNG images, which are small images, useful to also put in a presentation, but in a static way. And export all the images as PDF, which are the same high resolution that I was showing for individual frames. And then we can start this. And now it's gonna export the 263 frames with the same settings. So I'm gonna pause the recording because that may take a little while. Okay, so we have now advanced a little bit in our export process. It's not finished yet, but we have done 8% of our rather large data set. So we can have a look at what has been created. If we go into our project, now we have a number of PDFs, which are here, image 2, 3, 4, and so on, okay, plus the few ones that we had done before. If I open PDF, I see that when I export them as bulk, we see the vectors at the beginning being tiny. There was no movement, but they are named with the image number and the time. So it's useful to assemble. Okay, so if we go to image 10, for example, we see that this was the time 100 seconds, and in this experiment we have deformation being accommodated on this fold zone here and a little bit on this one, okay, but not much. Now we can also look at the PNG files, preview. So they are pretty small, so it's a bit easier. We see that image 2, not much happening. 3, 4, 5, 5, it's starting to move. Okay, 6, 7, 8. And now we have a little bit of deformation on one side. More. And another thing that we can see on these images is that as we calculated the vector, we indicated that we wanted the region of interest to be updated. So what we do in this case is that we take the average value of the vectors along the edges of the region of interest, and we calculate the velocity norm. So when we request that the region of interest is updated, we calculate the velocity perpendicular to one edge, and we use that average value to advect the edge of the mask. So along this side, there's almost no velocity perpendicular to the edge, so the edge stays. Same on this side, no movement. Same on that side, there's no movement in any direction. However, along this edge, the piston pushes in a direction that is almost perpendicular to the edge, so this edge is advected, and this is what we see. If we move back, the region of interest is moving with the vector in the direction of the convergence. And so on. So these small PNGs are useful to place in the PowerPoint as static images. And the other thing that we are being currently constructed is an AVI movie file, but this is not yet done. We have only exported 15% of the dataset. So we can see that we can, with TecPIV, export a large quantity of images, which make the analysis of the model deformation easier.